The views expressed on Science for the People are not necessarily the views of this station, its affiliates, sponsors, or advertisers.
This week on Science for the People, we're heading out into the black for science in deepest space and our own night sky. Hello and welcome to Science for the People. I'm Desiree Schell and I'm joined now by Phil Plait. Phil is an astronomer, author, public lecturer, and science evangelist. After working for 10 years on Hubble Space Telescope data, he decided that talking to the public about astronomy was a lot more fun. And he's been happily doing that ever since on TV, radio, and on his Bad Astronomy blog for Slate.com. He's written 3 books: Bad Astronomy, Death from the Skies, and 2 to the 7 Nerd Disses, a significant quantity of disrespect. And he also hosted his own Discovery Channel TV show, Phil Plait's Bad Universe. It is wonderful to have you back, Phil.
Hi, thanks, Desiree. It's nice to talk to you again.
Okay, so there is so much big news in the astronomy world lately, and I will be honest and say I thoroughly don't understand it at all. So maybe let's start with this one. Can you please walk me through the recent discovery of direct evidence of inflation, starting with what inflation is?
Yeah, this is the one that was probably the most difficult to understand of all the stuff going on right now. And that's because it's dealing with concepts that are kind of hard to wrap your brain around. Right now, we know that the universe is just shy of 14 billion years old. We also know that it's expanding. That's something that's been known for a century. And what that means is that if you run the clock backwards, it was smaller in the past. And 14 billion years ago, basically all of space and time were squeezed into this little dot and then exploded outward. You can kind of think of it that way. There are a lot of details to that and a lot of misleading stuff to that. But if you think of it that way, it's not horrible. And that's the moment we call the Big Bang. Well, it turns out the smallest razor's slice of a second after that moment, for some reason, while the universe was expanding, something happened that made the universe kick into high gear. It had this super accelerated expansion for an extremely tiny fraction of a second. And that period is called inflation. Now, we don't have any, or we didn't have any direct evidence of this, but the idea came about because of some things we see in the universe. We'd expect it to be kind of lumpy on really big scales, and it turns out it's not. It's actually quite smooth when you look at it on really big scales. And there were some other things, and these folks came up with this idea that maybe there was this period of inflation, and it's kind of like having a wrinkly bed sheet and then stretching it tight, and that gets rid of the wrinkles, and that's why inflation was thought of. Well, it turns out that there are a lot of predictions that inflation makes that if you observe the universe very carefully, you might be able to see or not see if it's wrong. And one of these predictions was that there would be these things called gravitational waves. And these are literally ripples in the fabric of space. Space itself expands and contracts like a wave moving down a slinky or an earthquake moving across the ground. And this would leave sort of its imprint on the light of the Big Bang. And we can see that light now. It's very far away, and it's cooled off a lot in 14 billion years, but we can see it. And in fact, they looked and saw the pattern predicted by inflation. The observations are really good. They look solid. I mean, when you look at it, it's like, yeah, whatever they're seeing is quite real. The question right now is this what they're seeing? Are they seeing these ripples from inflation, or is there something else that might have caused this? We don't know yet. It looks really good, I'll say that. There's a little bit of follow-up that has to be done, and I think this is going to hold up. But if it does, it's proving that these ideas of inflation are correct, and we have a whole new era of the universe to take a look at and try to figure out.
So if it isn't direct evidence, what could it be then?
Well, this light from the Big Bang has been traveling for a long time. It's been traveling for 13 billion years, and it's not without obstacles, roadblocks, speed bumps. There's stuff in the way, galaxies, dust, all kinds of stuff. And as it travels here, that light gets modified, changed a little bit. And it's possible that what they're seeing, this weird, what's called B-mode polarization, this could have happened because of something else. It may have been magnetic fields in giant clusters of galaxies and all kinds of other stuff. Once that is all straightened out, we'll know better about what's what here. But again, it seems likely that what they have found is, in fact, the fingerprints of inflation.
Okay, well, obviously, direct evidence and more evidence is better. But does this actually change anything beyond that?
Well, it does have implications for how we study the universe. I mean, first of all, if this holds up, you're going to have a lot of cosmologists, people who study the universe in general. They're going to be scrambling to their blackboards trying to figure this out. Also, because we want to know more about this, we'll be building different kinds of telescopes to try to observe it better in more detail. If this pans out, then that means, oh, look, these predictions these people made are wrong, so we don't have to look at those anymore. And these predictions over here make more sense. And they're also saying this. Well, maybe we can observe this if we build this new kind of telescope. So basically, anytime you discover something new, it sort of guides how you try to figure more things out later. And also, you can divide up the history of the universe into these different sections: the Big Bang, inflation, the modern era, and a few others. And this is one we really didn't know anything about. And if this works out, hey, look, this is, the door is cracked open on it. We can take a peek inside, try to figure out more about what's going on, and get a bigger, more complete picture of the puzzle that is the history of the universe.
Okay, now you and I had this interview set up previously, but in the time that we set that up and today when we were actually going to talk, there were two other astronomical developments. And since I have you on the line, I'm going to force you to talk about them. So what were you doing today?
Yeah, we had to push back the interview twice because I was so busy hunched over my keyboard writing about this. There were two really interesting solar system discoveries that were announced today. One is that an asteroid has been found that has rings, and that's really cool. We know that, of course, Saturn has rings, the big planet Saturn. It turns out Jupiter has thin, faint rings. So do Uranus and Neptune. All four giant planets in our solar system have rings. But we don't know of any other objects that have rings in the solar system. And it turns out now we do have another object with rings. And it turns out it's a weird kind of asteroid. It's an icy, rocky object called Chariklo. I have no idea if I'm pronouncing that correctly, but it's probably close enough. And it has a weird orbit that keeps it out past Saturn. And it's a part of a family of objects called centaurs, because a centaur is, right, half human, half horse. And these objects are sort of half comet, half asteroid, half rock, half ice. We know of quite a few of these centaurs orbiting the sun. Chariklo is about 260 kilometers, or about 160 miles in diameter. And it's like the others, probably a mix of rock and ice. Now, what happened is that this object happened to pass directly in front of a star as seen from the Earth. And when they do that, it blocks the light from the star. And this was known in advance, and so a bunch of telescopes were looking at it. And what they do is they do this from different locations on the Earth so that each of them sees it from a slightly different angle. And that way you can get the diameter of this object as it passes across the star. If from one position you only see that blocking of the light for a minute, in another position you see it for 2 minutes, that means it's twice as long in one spot than another. The object itself, you're seeing its shape. And that's really cool. If it's a circle, if it's lumpy, or if it's squished or potato shaped or whatever, you can kind of tell. And what happened was, instead of seeing it block the starlight and just the starlight going bloop, gone, and then bloop, coming back on, they actually saw the starlight dip a little bit, then dip a lot, and then it was gone, and then it came back, and then it dipped a lot, and then it dipped a little bit again. So it's like little, big, 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 little dipped in the light. Now, you could say, what could have caused these extra 4 dips? And it's like, well, maybe it has moons. We know asteroids have moons. But then they would have to be perfectly lined up, a little one, a big one, and then another big one and a little one on the other side. And that doesn't make a whole lot of sense. That doesn't seem likely. But we've seen stuff like this before, and it turns out rings do this. In other words, this object has a ring system, 2 rings, a broad one and a thin one. When the thin one passed in front of the star, it blocked a little bit of the light. When the thicker one blocked the starlight, we saw a bigger dip. Then the planet blocked the light, or the planetoid, the asteroid, and then the big ring, and then the little ring again. That's why you get these 5 patterns of dips. And we've just never seen this before. And the observations I saw, they're great. They look perfect. I mean, there's very little doubt that that's what we're seeing here. Probably this formed by a low-speed collision. Something hit Chariklo and caused it to be enclosed in a cloud of dust, which then settled down into a disk and formed these rings. And it's even likely that it has a dinky little moon that we didn't see that is sort of gravitationally sculpting these rings into 2 separate broad rings like this. So it's really cool. I mean, you're just looking at a star and the starlight fades for a few seconds or whatever, And the next thing you know, you've got a brand new kind of object, an asteroid with rings, and a moon that we didn't even detect, but is kind of implied.
So is it likely that there are more asteroids like this out there?
Yeah, there's not much reason to think that this is a recent event, an unlikely event that we just happen to catch. It's probably a ring system that's relatively stable and, for all we know, could be millions of years old. If that's the case, then once you form rings, they stick around. And that means that if there are more of these objects out there that got hit by another asteroid, and we see that happening, it's in fact likely that we will see more of them as time goes on, that we'll discover more.
Okay, but that is not the only thing that happened. What else? This one is a bit of a debacle, so I'm
Yes.
excited.
This one had me banging my head against the desk today. Astronomers have found a very distant object called 2012 VP113, and it is an ice ball, probably something like 500 kilometers across, 300 miles across, that orbits way past Neptune. This is one of the most distant objects ever seen in our solar system. And it's really interesting because it is very far away. There's only one other object we've seen this far away called Sedna. And both of these objects are out way past Neptune. Now, you know about the planets in the solar system. If you want to call Pluto a planet or not, I don't care.
We're not
But
getting into that.
Neptune's about 30 times the distance that the Earth is from the sun. And it turns out there's a bunch of little ice balls out there that orbit the sun from about Neptune's orbit, 30 times Earth's distance, out to about 50 times Earth's distance. And we know about these things. We've known about them for about 20 years now. There are a lot of them. But we think, we're pretty sure, there's another population of objects, a giant cloud of these things called the Oort cloud, named after the astronomer who first basically figured this out mathematically. But we hadn't really seen that many examples of them. And then Sedna was discovered a few years ago, and it looked like one of these things. And now we've got VP113, and it looks like another one of these things, a totally new population of objects. The cool thing about this is that it is not the most distant object we've ever seen. A lot of people are saying that. Not true. Sedna is actually farther away from the sun than this thing is right now. It's not even the thing that gets the farthest away from the sun, because Sedna, again, gets farther away from the sun than this thing is. What's more important is that if you look at how close it gets to the sun and compare that to Sedna, Sedna gets closer to the sun than this thing does. In other words, if you took all the objects in the solar system and lined them up for distance from the sun, closest to farthest, and do that in terms of how close they can get to the sun, because some things orbit in ellipses and get closer and farther, you'd have Mercury, Venus, Earth, Mars, a bunch of asteroids, all that kind of stuff. VP113 would be the most distant thing. In other words, the closest it ever gets to the sun is farther than any other object we've ever seen. That's what makes this thing cool.
Okay, so it's the farthest, but is that the farthest that we can see?
No, and that's a very good question. The neat thing about this, there are a lot of neat things about this. One is that this thing is fairly big. At 300 miles, it's decent sized. And you got to realize it's also ridiculously far away. 10 billion miles, something like that, something crazy like that. And we're seeing it with big telescopes. If there are bigger objects than this, and there's no reason that there shouldn't be, we should be able to find them even if they're farther away. Now that we've seen this, we know they're out there, which means people will be looking even harder for these things. So that's cool. And the other cool thing is that the orbits of Sedna and VP113 are a little strange. They're elliptical, but they shouldn't be as elliptical as they are. And we don't know exactly how these things form, but it's possible. I'm not saying it's likely. I'm not saying it's proven. I'm saying it's possible that there is another large object out there, something maybe even as big or a little bit bigger than Earth, that is gravitationally affecting some of these things. The reason we found Sedna and VP113 is because they get close enough to see. There could be a huge population of these things that never get that close. And so it's possible that, there's a planet out there or something big that is affecting these things, dropping them in closer to the sun. And since those are the ones that get close enough to see, those are the ones we find first. As we find more of these, we'll get better at this. We'll find out. So I'm not saying there's another planet out there because we don't know, but it's interesting. There could be.
Well, and, I do want to bring up the fact that this press release was put out about this, and it implied something entirely different, I would say.
The press release was a little oddly written, and it made it hard to figure out exactly what it was trying to say. Now, when you're saying something like, this is the object that gets farthest from the sun when it's closest from the sun, how do you...
Good point.
Right? It has the largest perihelion distance. is how you phrase that, actually. Perihelion is the point in an object's orbit where it's closest to the sun. And if you say it that way, it's a little less confusing, the largest perihelion distance. And that's what makes this thing very special. But if you don't read the press release very carefully, you might think this is the most distant object ever seen, or it has the biggest orbit ever seen, and that's just, neither of those is the case. I'm seeing a lot of that on Twitter. But to be fair, I had to do a lot of digging into the actual orbital characteristics of these objects to figure this out.
One of the things that I like so much about your articles on bad astronomy is that you understand that most of us are very self-interested, and we want to know, so what does this mean to me, personally, person who is not an astronomer? So, Phil, what does all this mean to me?
Well, it means that probably somebody you know or a friend of a friend will get more grant money. So that's good. You're probably not more than 2 or 3 friends removed. Anybody listening to this podcast is probably not more than 2 friends removed from an astronomer who's going to get money for this. I could say a lot of stuff. This inflation, cosmic inflation thing could lead to artificial gravity, or faster than light travel. You can say all that kind of stuff. And it's not really true. It's not true. You can't prove me wrong. But, it's not like, tomorrow we're going to have Starship Enterprises flying around the universe.
Oh.
And these asteroid things, they're not going to hit us. They're not going to wipe out life on Earth. They're not going to lead to a better flavor for toothpaste. But anybody who listens to this podcast, and honestly, anybody who is a living, breathing person living on this planet, should be interested in what's going on around them. We are a part of this universe. It made us. And we are looking out in it and trying to figure out why is the solar system shaped the way it is? Why are the planets set up the way they are? What's going on? How did it just so happen that we're here? Why is there something rather than nothing? These are very profound questions. And it just so happens that these discoveries are incrementally getting us closer to getting the answers to those questions. So it may not make your life directly a better thing, but it's going to make your life more fun to live just knowing this stuff.
You are so lovely, Phil.
Oh, thank you.
Thanks so
But
much.
I honestly believe this.
I know
I'm
you
not-
do. This
I'm
is
not
why we
blowing
invite
smoke.
you on the show.
People say that sometimes. Oh, you're just trying to be profound. And it's like, no, I read these things and I'm like, oh my gosh, this is so cool. And it's just wonderful to see people figuring stuff out. I think one of the best things about people is that there are really smart people out there, way smarter than me, way smarter than even other smart people I know. And they're figuring this stuff out. They're curious. They want to know. And the next thing I know, we know a little bit more about the universe. And then I get to tell other people about it. And that's my favorite thing ever.
Sing it, brother. And thank you so much for being here.
My pleasure. I hope we haven't run out of electrons here.
And we've linked to Phil Plait's blog, Bad Astronomy, on our website at scienceforthepeople.ca. And we'll be right back to talk about our ever-brightening night sky with Paul Bogard, author of The End of Night, Searching for Natural Darkness in an Age of Artificial Light. Stay tuned.
Science for the People is a weekly radio show exploring everyday life from a scientific perspective. To find out where Science for the People airs near you, or to listen to past episodes, check out our website at scienceforthepeople.ca. You'll also find links to connect with us on Facebook, Twitter, and Google+, or to subscribe to the podcast in iTunes. And now, back to the show.
Welcome back to Science for the People. I'm Desiree Schell, and my guest today is Paul Bogard. Paul is an assistant professor at James Madison University in Harrisonburg, Virginia, where he teaches creative writing and environmental literature. He's the editor of Let There Be Night, Testimony on Behalf of the Dark, and he's here to talk about his new book, The End of Night, Searching for Natural Darkness in an Age of Artificial Light. Thanks for being here, Paul.
It's great to be here.
This, sir, is a fascinating topic for a book. It's part science and part history and part travelogue, but it's also a very personal look at what darkness means to us as people. So what brought this on? Because there seems to be a trend in your writing.
Well, I mean, I think that it all stems from having the good fortune to grow up in Minnesota. I grew up in Minneapolis, and we've always had a cabin up in the northern part of the state, where I grew up standing on the end of the dock under the Milky Way and had that firsthand experience of a real night sky and a real darkness. And then I've had some once-in-a-lifetime experiences around the world as well. I write about one of those experiences in Morocco where I walked out of a youth hostel in the middle of the night and thought it was snowing, and it was just all the stars all around. And I think that these experiences, the cabin and then these other experiences, have made such an impression on me that when I began to look around for things to write about, my love for the night and for darkness came foremost into my mind, and things flowed from there.
One of the interesting things about the book is that most of us, we understand that there are varying degrees of dark. We can see that. But darkness actually can be quantified, correct?
Yeah, I mean, we're trying to, at least I would say. The scale I use in the book is something called the Bortle scale, which is a 9-point scale that quantifies darkness. There are also some other scales people can use. My friends at the U.S. National Park Service Night Sky team have come up with a 100-point scale to rank darkness. So we're trying, because people like to quantify stuff, and it also helps us understand what we have and what we're losing.
Is that done mainly for astronomical reasons?
I think that's the original part of it. The Bortle scale that I use in the book comes from a man named John Bortle, who's a longtime amateur astronomer who got tired of younger astronomers calling him up and inviting him out to what they thought were dark areas. And he would get out there and realize that these younger folks really didn't know what real darkness was. And I guess he meant real dark skies. So we're concerned especially with the light in the sky as an indicator of our loss of darkness in general.
Well, why is it so difficult to tell the difference between the different kinds of darkness?
For example, with the Bortle scale, where you have 9 to 1, you can tell the difference pretty easily between, say, a 9, which might be something like a Las Vegas or a Times Square or a major, downtown Toronto or Montreal, something like that, and say certainly a 5, which would be maybe a suburban sky, or definitely like a 2 or 3. The tough thing is, what's the difference between a 9 and an 8 or a 9 and a 7? Where are the gradients? And when it comes to losing darkness, I think one of the keys is that if we could compare the nights we experience now with, say, the nights we once experienced, say, 30 years ago, I think most people would be alarmed and would say, wow, what's happening? But what's happening is that we're comparing the nights we experienced tonight with what we experienced maybe 6 months ago or a year ago, and we can't tell the difference, essentially.
So you say in the book that most of us never experience the darker end of that scale.
Yeah, that's what I've been told. One of the stories I tell is when I went out with the Park Service team, I was in Death Valley with Dan Dorisco, one of the guys, and we had a phenomenal night. I mean, it was one of those nights, and I write about it in the book, where, I'll never forget it. It was so beautiful. And yet, on that scale of 9 to 1, Dan said this would be a 2, because we could see the light on the horizon from Las Vegas and in other places from Los Angeles. And it's just, he said he'd done measurements in over 200 different locations and only given 3 spots a Bortle scale 1 ranking, just because there is so often on the edge of the horizon or somewhere out there a light you can see. It's just really hard to get to a place where there's no artificial light.
Well, do ones exist?
Well, when I first started researching the book, I asked Chad Moore from the Night Sky team, where could I go to experience a 1? And he said, Australia would be a great start. And I said, well, Chad, I was thinking in the lower 48. And he said, you might get lucky. There might be ones left. I think, if we're talking about up into Canada, certainly there are Bortle scale 1 skies, natural skies left. But my concern was really, what's the darkness like in the places where most of us live? What are we experiencing when it comes to nighttime? Or what could we readily experience? Where could we get to? So I spend a lot of time in our national parks and places that we already love, places that we could get to, rather than saying, hey, if you want to get to dark, you can go to the Arctic or the middle of the ocean. I just don't think a lot of people are gonna do that.
So then why exactly is it that we won't reach ones or even twos or threes?
Mm-hmm. Yeah, I mean, it's our use of artificial light at night. And I'm always quick to say, that artificial light at night is not the problem. It's how we use this wondrous resource. I mean, we're going to have light at night. We want it, we rely on it, and it's a pretty amazing thing. It's just that the way we use it is so often irresponsible, unthinking. We're just spraying light all over the place, up into the sky, into our eyes, into our neighbors' houses. It really just doesn't make any sense. And I think one of the reasons I'm really optimistic about dealing with this issue is I think that once people start to see light pollution and see the way we use artificial light in this kind of willy-nilly, all over the place style, we'll pretty quickly say we can do better. We can direct our light downward only where we need it. And people will see that the way we do it now is just wasteful and unnecessarily so.
Now, you use the term light pollution. Can we define that?
I define it as the overuse or misuse of artificial light at night. And within that sort of umbrella term, I like to break it down into three other terms. The first is sky glow. Anybody who lives in a city or a suburb will know it's that peachish or pink glow over a city, especially on a cloudy night, where the clouds are lit up by our lights. Second would be glare, that those lights that are just, again, shining in all directions, especially into our eyes. And then third, and I love this phrase, light trespass, which is essentially light that we're allowing to spread from one property onto our neighbor's property. So I know for sure in the States, and I'm sure this is true in the cities and suburbs in Canada, that we have, it's one thing to light up your property, but then we seem sort of unaware of the fact that we're also bathing our neighbor's house in our lights as well, and that's called light trespass. So all those things together is what we mean by light pollution.
So now that was a term that was originally used by astronomers, again, but people in a number of fields are actually worried about light pollution now.
Yeah, absolutely. And I think that, astronomers do wonderful work. Amateur astronomers are often in the lead in talking about light pollution, but increasingly it's folks like sleep researchers, cancer epidemiologists, environmental wildlife specialists who are calling attention to the way that artificial light at night, and especially, again, our overuse and misuse of it, is a completely unnatural thing, and that it's having real consequences to us for our physical, mental, and even spiritual health, and for environmental health.
This is Science for the People, and I'm talking to writer Paul Bogard about his book, The End of Night, Searching for Natural Darkness in an Age of Artificial Light. Let's dig into some of the concerns that you mentioned. In your travels, you looked at how wildlife was being affected by light and darkness. So what did you see?
Well, it's having a pretty profound impact. I would make that argument. I would also say that the research on this is so very new. I mean, I was giving a talk last night, and I made the point that it's really, we've seen a real growth in the research just in the last 5 years of the impacts of artificial light at night on the environment. But one of the things that made a real impact on me when I was writing the book is somebody said to me, all life on Earth evolved with bright days, but also with dark nights, and we need darkness. And it's just doesn't make sense to imagine that we could flood a given habitat with artificial light and not have an impact. If people have heard about this, they've probably heard about either sea turtles, for example, in Florida, that over hundreds of millions of years have evolved to come onto the shore and lay their eggs. And when the hatchlings come up out of the sand, they've evolved to scurry toward the brightest light on the horizon, which for hundreds of millions of years was the starlight, the moonlight on the ocean. But now, of course, it's the condominiums behind them or the streetlights, and they're paying the price for that. And the other thing maybe people have heard about are migratory birds. We have in North America more than 400 species of birds that migrate at night and are drawn off course by our lights with often real devastating consequences. So, but we also have, and this is less well known, we have more than 60% of invertebrates and 30% of vertebrate species are purely nocturnal, and so many others are crepuscular, so they're most active at dawn and dusk. And again, to think that we could flood their habitat with light and not have an impact seems foolhardy to me.
Well, there's also an impact on insects.
A tremendous impact on insects. And again, so many of those are those nocturnal invertebrates. They are drawn to light so often. And what researchers have found is that our lights at night act as sort of a vacuum within an ecosystem, kind of hoovering the protein up out of the ecosystem. And for example, if a new light is installed, we've all probably seen in the summertime lots and lots of insects flying around a new light. And what they've found is that at first, for the first few years, that we see that, but as the time goes by, fewer and fewer insects are drawn to those lights, and they've discovered that those insects, that protein, that really important part of the food chain is being sucked dry by these new lights, with an impact on all the species that rely on those insects.
I think it actually behooves us to mention that moths are far more important than people realize.
Yeah, this is something I didn't know much about, and I think, as you said, that most of us don't know. But moths are vitally important to ecosystems all over the world. They're important to us. They pollinate many of the fruits and flowers that we enjoy. They are nocturnal butterflies, as one person described them to me as, and they serve as a food source for so many other creatures as well. So to imagine that, moths are somehow just these sort of duncy insects that are, attracted to our flames, as we like to say, and nothing more, is really to miss how important they are to our ecosystems and to how they're suffering from all this light at night.
And so we have these detrimental effects that pretty much no one disagrees with in terms of its effect on wildlife. But we humans still tend to want more light, not less. So increasing or conserving the darkness is usually a tough sell for most people, correct?
Yeah, I think it is. Again, I'm optimistic about it. I think that most people just aren't aware of the costs from light pollution, from our overuse and misuse of light at night. I think one of the most compelling reasons to become aware of light pollution are the human physical impacts. I usually describe them as primarily three. One is they're impacting our sleep at night and contributing to sleep disorders. And sleep disorders are tied to every major disease that we're dealing with in the Western world. They are confusing our circadian rhythms, those internal rhythms that orchestrate our body's organs and the health of our bodies. And maybe most concerning is that they are impeding the production of the hormone melatonin, which is only produced in the darkness. And this lack of melatonin in our blood has been linked to an increased risk for breast and prostate cancer at night. So like the research on the impacts on wildlife, this research is very new, but it seems especially compelling. And as one guy from Harvard told me, he said, I think we are, with our understanding of light at night, where we were with our understanding of smoking in the 1950s. So
that is a bold statement, sir.
Sure, and I'm repeating what I was told by folks that I trust, and they were clear with me. They said, "Can I tell you that light at night gives you cancer?" No, of course I can't say that, but the evidence seems to be moving in that direction. And as they said, I sleep in the dark, and I would encourage you to as well.
Well, where there is more established research is around shift work.
Yeah, it's true. I mean, and where the studies have been done tends to be on the shift workers primarily, especially nurses working the shift. We've got enough evidence now that the World Health Organization considers shift work a probable carcinogen. So that seems pretty compelling to me. And again, one thing about shift work and these possible links is that more and more of us are working at night. We live in a 24/7 society, and we require that. As one ER nurse said to me, we can't just say oh, you're having a heart attack. Sorry, the hospital closed at 10 o'clock, right?
Right.
We're gonna have these resources available. So light at night is changing and is going to change. The coming of LEDs is going to make a significant impact on our experience of light at night. And I think it really behooves us to understand as best we can the impact of all this light on our bodies and our ecosystems, and then to be able to make good choices about what kind of light we're going to have at night.
Well, one of the things I found most interesting about the book was your exploration of how we link safety and light.
Yeah, it's such an important issue because I think that, especially if you're first introducing these ideas to folks, they may say, I hear you, but don't we need all this light for safety and security? The easy answer is no, we don't. We need some light, and again, we're going to have light at night. Light at night helps us at night primarily by increasing our visibility. But simply from, thinking about that, if you have very bright lights that are shining into your eyes and making it harder for you to see, that's not increasing your visibility. So a real reason that I'm optimistic about this is because the same kind of corrections we can make with our lighting to, say, take the light out of the sky and bring back the Milky Way are exactly what we want to do to improve safety at night, which is namely to shield our lights so they're only shining down where we need them and not into our eyes.
But one of the distinctions you continue to make in the book is it's not just the idea of decreasing the amount of light. Where do we need light? And specifically in this instance, I'm talking about the fact that we keep linking the idea of crime and light, but it looks like there's not the connection that we thought there was.
There really isn't. I mean, I like to say, there seems to be no compelling evidence that would say more, because some light can help us be safer and more secure at night, ever more light will make us ever more safe and secure. And in fact, there have been studies that have shown it's the reverse, that it actually we might be safer with not having so much light. And again, I think the evidence that folks gave me about, and some of the stories folks gave me about, how does it help us to light up our buildings at night, our warehouses, our office buildings, and then leave? What makes us safe at night and makes us secure at night is, again, visibility, either being able to see where we're going and who might endanger us, or to see the places that we want to protect. And too often we just light everything up as brightly as we can and then go inside and forget about it. That's not making us any more safe or secure.
I like the point you made about that criminals need light too.
Yeah, that's one of the funny things, I guess funny in a way that folks told me, is they made the point that, criminals are as scared of the dark as we are, and they prefer to have light both because of that fear, but also because light at night allows them to case their victims, whether it's individuals, people, or property. They like to be able to sit and watch and see who's coming and going and where they're going. They like to be able to plan their escape routes, that kind of thing. So this notion that, criminals are hiding in the dark everywhere and that they love the dark, I think is at least worth questioning. And I think when you start to think about it, doesn't make too much sense.
What's so interesting is we have these facts, but there is some kind of innate need that humans do have for darkness, something that can't be quantified or tested. And it's definitely linked more closely to philosophy than it is to science, isn't it?
I think so. And just to make the bridge from what we've been talking about, we have humans have a fear of the dark, and I really think that when people, I admit that in the book I have a fear of the dark, and I'm the guy who wrote, The End of Night. I think the difference for me is that I have so much respect for darkness now. I understand how important it is, and as you say, we have benefited from darkness forever. It has allowed us to have times of contemplation, to have times of meditation, to have times of beauty. You think about the light at night that is so beautiful, whether it be fireplace or campfire or candlelight or starlight, certainly. And all this beauty needs darkness in order to shine, as it were. And I think that we have benefited in our arts and our philosophy and our religion, our spirituality from experiences of darkness. And again, to think that we could do away with it and not have it affect our souls, our spirits, our minds, it seems to me really short-sighted.
Yeah, we can't measure that.
No, it's impossible to measure, and these are the intangible values. And unfortunately, we live in a society that's obsessed with measuring things, and that somehow if you can't measure something, it doesn't have value. But I don't think at heart people really believe that because you can't measure beauty, it doesn't matter. It's vitally important to what it means to be a human being, and darkness and nighttime are really important to us.
You're tuned into Science for the People, and I'm talking to Paul Bogard about his book, The End of Night, Searching for Natural Darkness in an Age of Artificial Light. And we'll be back with more of that after this.
On the next episode of Science for the People, we're looking across the periodic table and assessing the scarcity of modern society's essential elements. We're joined by Dr. Thomas Gradel, director of the Center for Industrial Ecology at Yale University, to talk about the rare metals that play a role in our electronic devices. We'll speak to physics professor Dr. Moses Hungwai Chan about our dwindling supply of helium. And we'll talk about the phosphorus that plays a critical role in modern agriculture with ecology professor Dr. James Elser, co-organizer of the Sustainable Phosphorus Initiative at Arizona State University. That's next week on Science for the People, on your local radio station, or online at scienceforthepeople.ca.
Welcome back to Science for the People. I'm Desiree Schell, and I'm here with Paul Bogard, the author of The End of Night, Searching for Natural Darkness in an Age of Artificial Light. Okay, so there are a lot of people in a lot of different fields that are attempting to conserve the dark. Can you tell us a bit about what people are working on?
Sure, absolutely. We have folks all around the world who are working on this issue. Again, the big part of it is to raise awareness. Just, most of us aren't thinking about this. If you're under 30 or 40 and you live in the Western world, you've grown up swamped in light. You don't know that there could be any difference. So we're just trying to raise consciousness about nighttime. And some of the things that we're doing, that folks are doing that I talk to in the book are things like working with local councils, local government, state government, provincial governments to incorporate lighting rules or lighting ordinances so that especially any new light that's installed doesn't add to the problem. It's hard a lot of times to go back and ask folks to change out their light or change the way they're doing things, at first at least. But if we can make sure that any new light doesn't add to the problem, that's a real step forward. There are also lots of efforts to conserve and preserve the dark areas that we have left. So we have dark sky areas, is usually what they're called, or starry night, starry sky areas, where people have recognized that, hey, this is a wonderful resource we have. It's worth something. Let's protect it. Let's change the lights that we need to and make sure they're not shining up into the sky. And any new lights that are put in don't add to the problem.
And can you talk about some of the technology that we're seeing? I love the idea of the responsive lighting.
Sure, and again, this is exciting. It's reason for optimism. It revolves around the coming of light-emitting diodes, or LEDs. What I was told when I was researching the book is night is going to change, and light at night is going to change, primarily because of, as one guy said, the coming tsunami of LEDs, just that they're going to be everywhere. And the reasons for that are good. LEDs tend to be much more efficient than the light we use now, the electric light we use now, and they are also much more potentially highly programmable. That is, that a city could install all new LED lights and have them with what we call adaptive controls, could have them connected to a computer and could program, say, at 1 o'clock in the morning, the lights go down 10%, and at 2 o'clock in the morning, they go down another 10%. So you're reducing light where you don't need it, when you don't need it, saving money, saving energy, reducing light pollution. So that is the promise of LEDs, which is reason for optimism. peril of LEDs, and I think it's worth talking about this a little bit, is that because they are so much more efficient, we may just, as we do with efficiency, think, well, let's just use more of it.
Right.
So there have been instances where cities have retrofitted or replaced their electric lights with LED lights and seen their light pollution grow by 2 or 3 times, which is really unfortunate. And the new LEDs, or the LEDs that folks are tending to put in now, also tend to be heavy with the blue part of the light spectrum, which is the part of the lighting spectrum that concerns folks, researchers most. So LEDs are not a panacea. They are not just the answer to everything, but they could be a real important part of the future.
Well, that's what I was wondering, if at a certain point this might just be self-solving, because the higher oil prices go, the more people are interested in lowering their energy use, usually.
No doubt about it. And I think that, right now, one of the reasons that we waste so much light is because it's so cheap. Electricity is artificially priced. It's artificially cheap. We don't pay the full price of it. And so we think it's cheap. And so we can blast our lights all night. Actually, several folks told me while researching the book that they're convinced, for example, that once we start driving electric cars and we're plugging our cars in all night, you will not have cheap electricity anymore. That certainly the price will go up, and then lo and behold, people will look around and say, hey, maybe we shouldn't, waste light like this at night. So that's, I think, again, a reason for optimism. Also, people have told me, let's get good lighting in the building codes so that, just in the same way that we build a new building, we do certain things just as a matter of course. We'll have lighting be part of that as well. We just won't allow, light to be wasted and misused as it is now. So another good reason to be optimistic.
You spoke to a number of lighting designers and how they work in sort of urban centers, and those conversations were fascinating. I have never heard anybody be so deeply enthusiastic about lighting.
Well, I hadn't either, and I learned a lot. It was really fun. I think whether it's in Paris and France or in Boulder in Colorado, and certainly there are designers now all over the world who are doing really fantastic stuff with light. It was fun to hear them talk about the possibilities for especially using LEDs and the kinds of things that we can think about. I remember in Boulder, one person telling me that, we can move away from having light poles, for example. I mean, think of something we just completely take for granted, that we have lights up on poles. And she said, a lot of roadway lighting, we don't need lights on poles. We can put lights into the street. We can put lights on lower poles or not even poles at all. It's just the things we can do. Paris has a new lighting design that's designed to cut emissions and energy use by 30%. And they're doing amazing things like figuring out, where are people at night in Paris and when are they there? We don't need the same level of light at 3 o'clock in the morning in a neighborhood where there isn't anybody that we do at, say, 10:30 at night in the main part of the city. So let's not have so much light. We have the technology to do that, and why not do it?
Now, you traveled all over North America for these stories. So, we have to ask, what's the darkest place that you found?
I think the darkest place I found was the western U.S. In the national parks there. I wish I had spent more time in Canada because I know there are beautiful, wonderfully dark places up there. In fact, I've heard about them from some readers, which is fantastic, and obviously in other places around the world. But in the U.S., it's in the western part of the country, in the national parks especially, Utah, southern Utah, eastern Nevada, places like Death Valley National Park, Bryce Canyon, Great Basin, these places that we already love, that we already visit and know, that are still relatively dark. And the Park Service here has decided that darkness is in fact a resource that they want to protect. And I think that this is another reason for optimism, that if we can preserve these cores of darkness and help people become aware of their value, that anybody who visits these places, whether it be the parks here or the parks in Canada or different places around the world, will go back home to where they live and think, maybe we could light our cities, our suburbs, our towns, our villages differently and preserve and bring back some of the beauty of night.
Well, I'm going to ask you a question that is not scientific. So,
That's all right.
I'm wondering, how does it feel to be in a place that's approaching one?
It's pretty amazing. It's pretty magical. I was just speaking with an audience of students last night here in Virginia, so people primarily who are about 20, and I could tell, I asked if anybody had experienced something like this. I had described a 1 and a 2 and given my experiences, and I don't think there was anybody in the room who could say that they really had experienced that. There was one student who had been in Peru and had maybe experienced that, but it's this feeling of breathlessness, of being without words, of not knowing how to describe it. You have stars that are in 3 dimensions. You can actually see stars looking further away, some stars closer. You feel lit by starlight. It's almost dizzying how amazing it is as you're staring up at the sky. It really is, unfortunately, an experience that was one of the most common of human experiences, and now we've made it one of the most rare of human experiences, and I think it's really difficult to quantify what we've lost.
Well, I think that was one of the most melancholy statistics in your book was that 8 out of every 10 children born in the U.S. today will never experience a sky dark enough to see the Milky Way.
I think it's kind of breathtaking. As I say in the book, it's like having a statistic say that 8 of 10 kids will never run or play outside or, something, that, as I said, just used to be a common part of what it meant to be a human being and now is just not part of our life. And I think especially when we think about children, I think about my own life and how, as I said, that experience of standing under the Milky Way, I felt like it imprinted upon me. It just made me feel like this is what life is. This is what it means to be alive. And to imagine that our children aren't having that experience anymore, I think is heartbreaking.
Paul, thanks very much for being here.
It's been my pleasure. Thank you.
And we've linked to Paul Bogard and The End of Night on our website at scienceforthepeople.ca. This is Science for the People. And there's one last thing I wanted to talk about today, and for that, I need another astronomer. I'm here with Nicole Gugliucci, who works with CosmoQuest, a citizen science project. Welcome back, Nicole.
Hi, Desiree.
So, for the uninitiated, tell us a bit about the idea of citizen science.
Sure. So citizen science is any endeavor where people who don't necessarily have a science degree or a formal training in science are actually contributing to some part or some stage of the research of a project. This could be anything from, we have a long history of birders and bird watchers who submit observations to Audubon societies to track certain species, to amateur astronomers who use their telescopes to monitor variable stars or look for events like supernovae. What has come up in the last few years is the use of the internet as a tool to get lots of people involved in citizen science projects.
Well, then what kind of citizen science does CosmoQuest do?
So we are mapping the surfaces of several planetary bodies. We are mapping the surfaces of the Moon, Vesta, and Mercury. All of these objects have been visited with spacecraft that are taking images that are the highest resolution images that we've ever had of these bodies. In particular with the Moon, the Lunar Reconnaissance Orbiter has been mapping for several years and structures down to just a few kilometers on the surface. But there's a lot of data. So we need help going through the data. It turns out that humans are still far better than computer algorithms at picking out shapes. That may not be too much of a surprise to a lot of your listeners, but our eye-brain combination's really good at picking out circular shapes, especially when the lighting is tricky. And so we need people to actually map and measure and mark all of these craters and surface features.
And now CosmoQuest just published a paper about the accuracy of citizens versus experts at this. So can you just run us through that paper?
This is a paper that was led by Stuart Robbins at the University of Colorado at Boulder. And he did this huge comparison study of crater marking between humans, basically. This actually hasn't been done in depth before. For the last several decades of crater research, you usually had one researcher at a time marking the craters in a certain region. But they were never really checked against each other. It was kind of assumed that any bias from using one human versus another was only a few percent. So he first pitted 8 crater experts with a different amount of experience in the field, from 5 years to several decades, and found that there's quite a huge difference between the way different people mark the same image of the moon's surface, up to a factor of 2 difference in crater counts. So that is kind of a big deal in its own right. But then he looked at the contributions of our citizen scientists that have been using the Moon Mappers project at CosmoQuest. And once you've had a number of people look at one image, say 15 people may have marked through all the craters in a particular image, you average those results and you get the same results as if you average all the experts. So first of all, we're saying, hey, this whole history of crater research has some individual biases in it, but you can get citizen scientists to participate, and you can map a region of a planet or the moon or some other body a lot faster and with the same accuracy as if you had all these experts look at it.
Well, I should probably ask, why does one count craters?
That's a good question. At first, it's like, well, that's okay, we're counting things. But the number of craters on a surface tells us something about the age of the surface. You imagine that the amount of things hitting the surface of the moon is steady, or not steady, but some predictable curve over time. It kind of lessens over time as the solar system has less junk in it to hit the moon. You can imagine that a surface that has a lot more craters versus a surface that has a lot less craters is an older surface. And so this is used to get the relative ages of different surfaces on the moon. We can get more exact ages by actually taking samples, such as from the Apollo program, and doing radioactive dating of those. And we get the ages of the different surfaces of the moon, and we understand something about the history of the moon, the history of impacts of the moon, and of course that tells us something about the history and likelihood of impacts on the Earth, because we're right next door. So counting and measuring all these craters tells us a lot about the geologic history of a surface. And so this all has to be pretty precise, and changing that by a factor of 2 is actually quite a big deal.
How many craters are there versus how many have been counted?
There are millions and millions and millions and millions of craters on the moon. With the citizen science projects using the Lunar Reconnaissance Orbiter data, we count how many marks people have made, but because we have 15 or so people marking the same craters each time, it overlaps. So although we've had something like 2 million crater marks made on the moon, that adds up to a few 100,000 individual craters. But there are millions and millions and millions more craters left to look at. So we've just kind of starting the work, but we've been able to demonstrate that the work that you guys are doing, that everyone out there is helping us with after just doing the minimal training with a video, is just as accurate as an expert that's spent years on this.
Well, how might one help you count craters? Because apparently you need help, if they were so inclined.
So if you go to cosmoquest.org, and you can sign up for an account so we can track how individuals are doing. You don't have to give us any information besides an email address and come up with a username. And then you are ready to get started. You go to the Do Science page, and it'll list a whole bunch of possible projects you can do. So we have Moon, Vesta, and Mercury right now. We're coming up with another one soon, which will have some Hubble data from the outer planets, and a whole different set of tasks you can do. And you're presented with a training video. So we tried to put together these training videos to tell you how to use the tools in the browser. And then you get started. And if you're doing the Moon Mappers project, it gives you feedback along the way on how you're doing. But you just get started with marking, and you can share and talk about them in the forums. You can view we have many different hangouts on air and articles that explain the science that you're doing, so you can really kind of go down the rabbit hole any way you want.
Go do science, people.
Do science!
Nicole, always a pleasure to have you here.
So good to talk to you again. Thank you.
And we've linked to Nicole Gugliucci and CosmoQuest and their paper on the success of citizen science on our website at scienceforthepeople.ca. And since you're there already, please click the links to Twitter, Facebook, Google+, and iTunes, which will do precisely the things that you think they will. Thanks for listening, and see you next week on Science for the People.